The aerodynamic drag in a truck can be reduced by the use of an appropriate air deflector. A reduction in the drag coefficient from 0.96 to 0.7 corresponds to a reduction of how many horsepower needed at highway speeds of 65 miles per hour. Assume that air is 0.00238 slugs per cubic foot. So basically what I'm asking for here is how much less horsepower do you need to overcome drag by adding this deflector. Now, I'm sure for most of you, you've seen the top of a semi. They have this thing here. I'm still old enough to remember when these were introduced and you never saw a semi with them. And the first time you saw it, was like, wow, that's really interesting. Okay, so what do we have to do? There's a couple different ways to solve this problem. But it's basically calculating out the power to overcome drag at the case of overcoming the drag when the coefficient of drag is 0.96, as opposed to when the coefficient of drag is 0.7. And so as we've seen, our drag force is going to be the coefficient of drag times rho over 2 v squared a star. And this is just me rewriting our coefficient of drag equation to where the drag force is what we're calculating for. Now, we're not using, I hit my laptop, we're not using the frontal area, we're not using the planform area because it's not a streamlined body. We're not using the wetted area because it's not a ship or a blimp. So we will be using the frontal area here. Now, we don't have the area, but we'll be able to put this together in a way that things will cancel out. And actually, no, I take that back. We do have the area. If we go back, I'm sorry, I was looking at the wrong part of my notes. We know this is 10 feet wide and 12 feet high, and it's the frontal area, so that gives us our area. And so we can just straight out calculate this out. Now, I'm looking for the reduction in power, so we could sit there and go, okay, well, my power at 1 minus my power with the second state, that's going to give me my change in power. And that's the way that I am going to go about solving it. And so let's do that. So what is power? Well, power is the efficiency times the velocity times the drag force. Now, we are not given an efficiency in this problem, so we're going to just assume that it's 100% efficient. So the power at 1 is going to be the velocity at 1 times the drag of state 1. Power of 2 is going to be the velocity at state 2, drag of state 2. Now the thing to remember is V1 is going to be equal to V2 because we have the truck riding along at 65 miles per hour, and so we just have more drag to overcome in the second state, the first state, as opposed to the second state. And so then if I if I look at that, since my velocity is the same, and if I just drop this equation in for my drag force, I'm going to have P1 is going to be coefficient 1 times rho over 2 velocity 1 cubed, because we have a velocity and a velocity squared, times the frontal area. P2 is going to be that coefficient of drag 2, P3, 2, frontal area, and I'm just going to put these together and subtract them, because I'm trying to figure out what we've got. So it's the same velocities. We'll be able to sit there and go, okay, well, P1 minus P2 is going to be equal to rho over 2 V1 cubed AF. And since I pull that out of both of them, and then just C1 minus the coefficient of drag of 0.2. And at that point, we can just plug in our numbers. So 0.00238 slugs per foot cubed divided by 2. My velocity, I converted it for you in the problem. So 95.3 foot per second is roughly 65 miles an hour. We're going to cube that. And then our frontal area is just going to be 10 feet times 12 feet. Coefficient of drag in the first case is 0.96 without the air deflector, and we'll take 0.7 with the air deflector. So the change in power. Let's look at units first, because these units are going to be a little bit of a mess. Feet squared, feet to the third. Well, those feet cubed will cancel out those feet cubed, and then I'm going to be left with slugs times foot squared. Slugs times foot squared. Now we do want to put that into a force of pounds. So remember, 1 unit of force is a pound. It's equal to 1 unit of mass, foot, which is slug, foot per second squared. And so that means that a slug would be a pound second squared per foot is equal to a slug. And so our slugs then, we can put in there pound second squared per foot. And so that foot will cancel out 1 foot. So we have a pound times a foot. And then we have seconds cubed on the bottom, which will end up canceling out 2 of the seconds on the top. So we're going to be left with pound foot per second, which is great because that is a unit of power. And so if I calculate this out, that's 32,100 foot-pound per second. And we can convert that over because 1 horsepower is 550 foot-pound per second. And so when I bash all that together, that's a reduction of 58.4 horsepower needed to now overcome that drag. So it's a pretty significant amount of horsepower that we can save just by deflecting the air over the cab.